Firstly, let's start with the importance of analyzing and relying in the sample by referring to the general article. First, regeneration of historical practices. Scientists can identify the raw materials used in the sample. For example, identification of dyes or fibers solids can be revealed, whether it's from plants or animals. From that, scientists can infer technological innovations like over-dyeing techniques and specific fiber processing. Next, preservation strategies. Analyzing and light could reveal degradation pathway of dyes and fibers to determine preventive conservation to extend the longevity of the sample. Preservation can be done by customizing the chemistry of the original materials, such as control humidity, adjust the exposure, and avoid inconsistent conservation treatments. Moreover, from analysis of analyte, scientists can choose new techniques that are more efficient, such as DART-MS. It provides rapid analysis of characterization dye classes. Scientists also can overcome limitations in identifying specific isomers or complex dye mixtures. Last, scientists could resolve structural uncertainty. This is because plant fibers have similar chemical compositions. Relying on the compound alone will fail the experiment. Thus, from analyzing the analyte, scientists can consider advanced spectroscopy to detect molecular level
Next, I'm
differences.
going to talk about the technique used in this investigation. First, they use DART-MS, which is direct analysis in real-time mass spectrometry. The procedure starts by set up the DART-100 probe with SVP controller and couple it to a thermo-orbit elite mass spectrometer. Make sure gap between the DART ceramic cap and the MS inlet tube is 7 mm. Supplementary helium flow is 3.4 liter per minute using a vapor interface. After that, for a sample handling, using a methanol clean tweezer to pick up the tiny textile fiber in a few millimeter and expose it to 350 degrees Celsius helium gas stream from the dart source for less than 1 minute. Lastly, for detection part, alternating between positive ion mode and negative ion mode. Collect mass spectra from 100 to 600 mass per charge. Ion type detected mass protonated in positive mode and deprotonated in negative mode. Don't forget to collect background data before and after exposure. So, the reason why that MS is being used in the investigation compared to other method or other technique is because it fast and non-destructive screening of dyes on tiny textile fiber. No need for dye extraction or solvent, so it reducing chemical alteration risk. It's useful for spotting small dye-related molecules quickly, and it screens textile sample with minimal preparation. Ideal for cultural heritage study where sample material is fragile. Other than that, it allows rapid result for researcher to prioritize which sample need full LC-MS analysis, and it has high sensitivity to a wide range of small dye-related molecules. Second technique that being used in the investigation is LC-MS, which is liquid chromatography mass spectrometry. So, the procedure starts by sample preparation, which is dye and protein extract where it is suspended in 0.1% formic acid. For set up the LC, the injection volume must 10 microliter. Track column, a clamp PEPMAP 100. Analytical column, PEPMAP RSLC. Flow rate must 300 nanoliter per minute and the gradient over 60 minutes. Low organic to high organic solvent. For separating complex dye mixture. For MS setup, Orbit Trap Elite, there are two. For MS1 is full scan. The range is 375 to 2000 mass per charge, resolving power 60,000, and AGC is 1E6 and ejection time is 100 meter second. For MS2, which is fragmentation, top 10 most intense ion selected and resolving power is 50,000. HCD is higher energy conditional dissociation, 30% energy. Isolation with 5 mass per charge. Fixed first mass is 100 mass per charge, and make sure sample wash run between analysis to prevent carry-over. Second technique that been used in the investigation is LC-MS, which is liquid chromatography mass spectrometry. So, the procedure starts by sample preparation, which is dye and protein extract where it is suspended in 0.1% formic acid. For set up the LC, the injection volume must 10 microliter. Track column, a clamp PEPMAP 100. Analytical column, PEPMAP RSLC. Flow rate must 300 nanoliter per minute and the gradient over 60 minutes. Low organic to high organic solvent. For separating complex dye mixture. For MS setup, or big trap elite. There are two. For MS1 is full scan. The range is 375 to 2000 mass per charge. Resolving power 60,000. And AGC is 1E6 and ejection time is 100 meter second. For MS2, which is fragmentation, top 10 most intense ion selected, and resolving power is 50,000. HCD is higher energy conditional dissociation, 30% energy. Isolation with 5 mass per charge. Fixed first mass is 100 mass per charge. And make sure sample wash run between analysis to prevent carryover.
Next, I'm going to provide a discussion regarding the information that is gained from the spectra from the article and how the information can be used for quantitative or qualitative analysis. Now, firstly, here you can see a spectra of direct analysis in real-time mass spectrometry, where it displays mass to charge ratio of ionized compound released from the surface of the textile samples. Now here, indigotin was identified in blue and green fibers by its ion at mass to charge 263.083, confirming the use of plant-based indigo. The absence of 6,6-dibromo-indigotin ruled out blue dyes created from brominated indigoid like shellfish. Indigotin can be identified in green because green is a mixture of primary colors of blue and yellow. Here we can see a liquid chromatography mass spectrometry chromatograms, which it provides retention time and intensity of different dye after separation. Also, mass spectra will attach to each peak, which confirms the molecular identities via the mass to charge values. Now here is specifically to identify blue dye, where liquid chromatography mass spectrometry chromatogram revealed a strong peak at 9.81 minutes, identifying 2-carminic acid, indicating the use of cochineal insect like Dactylopius confucius. The supporting peaks of lactic acid, chromic acid, as well as leucidin showed that both animal and plant-based altequinones were used, indicating blending or sequential overlap. Lastly is the identification of yellow dye, where flavonoid is detected through liquid chromatography mass spectrometry, such as quercetin, merithimethin, alongside degradation products like 4-hydroxybenzoic acid. Based on the information gained from the chromatograms, we can now do a quantitative or qualitative analysis. Now, from a quantitative or semi-quantitative perspective, peak intensity and area under the curve in liquid chromatography mass spectrometry chromatogram offer insight regarding the dye abundance. For example, carbonic acid, which is present in red dye profile, had consistently had the highest peak throughout, which suggests that it is a dominant dye. However, plant-based anthraquinones were present in lower abundance, which indicates that it is a secondary or additive use. Similarly, in yellow or green samples, the relative peak heights of quercetin and butene compared to minor compounds such as sulforaphane allowed researchers to infer dominant plant dye sources. Extraction efficiency was also evaluated semi-quantitatively by comparing the same sample under 3 different protocols, which consist of urea, methanol, and isopropanol or ammonium bicarbonate. Urea extraction had yielded lower intensity peak, which shows that it is less effective for complete dye recovery. This observation had illustrated how the qualitative identification of dye classes and specific compounds was tightly integrated with semi-quantitative evaluation of dye proportion, dyeing techniques, as well as extraction method performance, all made possible by detailed spectral. Next is the advantages of this analysis. This analysis offers high sensitivity and selectivity, which can be seen through liquid chromatography mass spectrometry, as it allowed the detection of trace dye compound with high sensitivity even when few milligrams were used, as we are using ancient textile. Structural isomers such as leucidin and purpurine were distinguishable based on mass to charge and retention time, providing excellent selectivity. On the other hand, it also provides non-destructive and minimal invasive, as direct analysis in real-time mass spectrometry requires little to no sample prep, preserving the heritage of the sample, which is particularly important for a rare archaeological material. Next is the limitation that this analysis offers. Firstly, when it comes to low volatility of glycosides in direct analysis in real-time mass spectrometry, direct analysis in real-time mass spectrometry is ineffective when it comes to identifying compounds like carbonic acid in red dyes, as it offers low volatility and strong hydrogen bonding, limiting its usefulness for glycosylated dyes. Second, it offers incomplete quantitative analysis. While liquid chromatography mass spectrometry enables semi-quantitative insight via peak intensity, absolute quantification was not achieved due to lack internal standards and variability in dye degradation over time.
Moreover, the improvement of the limitations can be done by introducing internal standards. Adding aspect level standards could allow for absolute quantifications, helping to normalize for project effects and improve inter-sample comparisons. Second, expand reference libraries, building more comprehensive dye and protein databases, particularly for underrepresented species and dye blends, would improve identification accuracy and enable broader taxonomic resolutions. Lastly, the summary of the study are liquid chromatography mass spectrometry (SCMS) is the most accurate, sensitive, and selective. It enables to identify parties and peptides even in degraded or minimal samples. Meanwhile, data analysis in real-time mass spectrometry (MS) offers rapid, sensitive, and robust preliminary screening, but with lower selectivity and accuracy for specific compounds or isomeric mixtures. This multi-technique workflow balances speed, specificity, and preservation of the samples, with LCMS providing the most comprehensive and reliable data for both dyes and fibers.
That's all from us. Thank you and have a good day.